So today we have a new topic. I already published the module you should read and learn, but it's still incomplete. I had very little time to write everything down. So soon, probably tomorrow or a third day, I will complete this course with an additional section. But anyway, most of the stuff is already inside this module. It's about uh, laws and logic circuits. Basically, everything what you have to know about the laws of Boolean logic is already inside the module. The only stuff which is missing is the one about logic circuits. So please read this module as you already did with the previous modules. Hopefully, there are examples, lots of examples, and there is also stuff you have to read, you have to understand. Uh, this particular part is particularly dense, a little bit. But I'm going to talk about this stuff now. You can find exercises here as well and further examples at the end. Okay, I will also complete this closing test. You should play, you should complete, but this is still incomplete. I will let you know if I did everything I planned. Okay, so this is your duty till next week. Okay, so now I will talk about the laws of Boolean logic. Let's see what the goals are. So you already experienced that logical formulas can be quite long. They can be quite complicated. Therefore, it's always a good idea to simplify them. The laws we are going to learn about can be really nicely used to simplify formulas. You will see that. Furthermore, it would be nice if we could check if formulas are tautologies, I mean logical laws, if they are satisfiable, if they are unsatisfiable, and also if they are logical consequences. So far, we only learned the algorithm of truth tables for that, right? So I don't know if you like truth tables or you hate them. I actually don't really like them because uh, for a very short formula you can get a very huge table. We already talked about this. For example, if your formula contains only 5 variables, your table will have 32 rows. If you have 6 variables, so one additional variable, then the table has already 64 rows, and the size of the table uh, increases exponentially. So this is the drawback of the truth tables. Therefore, there must be some better approaches, and in the module you find such an approach in this section, semantic analysis of formulas. This shows you another approach how to analyze formulas. Sometimes, not always, this does not always work, but sometimes this works. If you look at it, it looks really ugly, it's complicated, and I'm telling you, it's not that straightforward how you can check, for example, if a formula set is satisfiable, or how you can check if a formula, for that this long formula with three variables is satisfiable, a logical law again. This second approach works. It's better. I think it's better than the algorithm of truth tables, but not really intuitive, and it's not easy to use. Therefore, now we learn about a third approach, which is based on the laws of Boolean logic. So this was the one I was talking about. So what this is about? It is about certain formulas which are equivalent to each other. So for example, let me show you this one here. So you already know that double negations can be eliminated. So this is one of the, this works as a simplification rule. This based on the fact that negation P is equivalent with P. We can show that very easily. Or let's see another rule like this one. This is a very nice rule. I will talk about it more. So for example, if you have such a structure in your formula, two formulas P and Q are connected with conjunction, and this stuff is connected with Q again by logical OR. So Q appears outside of the parentheses and inside as well. Then you can just simplify this part out. Only Q remains. This is a very nice simplification step. So basically you can just throw out the most of the majority of the formula, right? And again, this simplification step is based on the fact that this formula is equivalent with this formula here. So there are so many such well-known logical laws. I have actually 5 slides about them. In the lecture notes you can find this kind of huge table, but actually the content is the same. Okay, so let me just talk about a few more laws, and after that we will do an exercise together. I will simplify this formula, and also we will find out if this formula is a logical law or satisfiable or logical contradiction. Of course, meanwhile, if you have any question, just raise that question and I will be happy to answer it. So let's see. So there are kind of obvious logical laws here. For example, how can I? Okay, let me just erase this slide first. Okay, so this one can obviously be simplified to this one. So if you have a logical AND or logical OR, the node applications are necessary, right? So this is really obvious. Or you already know about associativity. So this was part of the quiz, and well, most of you couldn't answer that question correctly, so maybe it's a good idea to recap what we should know about associativity. So associativity means Actually, you can put these parentheses anywhere. If you have two conjunctions, it doesn't really matter if you evaluate this part first and then the outermost conjunction, or you evaluate this part first and then the outermost conjunction. So basically, the order of evaluating conjunctions after each other, it doesn't matter. And the same holds for this junction. So you already uh, knew something about associativity, right? And similarly, I'm pretty sure you already knew that you can exchange the order of the two sides of a conjunction or a disjunction here. You can freely exchange the order of operands. It's quite obvious. Okay, double negation is also obvious. Absorption, I already mentioned this one. It's not that obvious. So this is something we should think about, or rather, we could try to prove that this law holds. We can just prove that the two sides of this equivalence are actually equivalent. Actually, this is proved here in the lecture notes. So please later check out this table. It explains why these very nice laws of absorption hold. Okay, let's move on. I'm pretty sure you already met this guy here. So if you connect something and the negation of that something with conjunction, then this is definitely false. This is what we call the law of non-contradiction. Actually, in philosophy, it comes from philosophy. And similarly, if you connect something and the negation of that thing with disjunction, then this must be true all the time. The name of this law is the law of excluded middle, also from philosophy. These are very nice rules. These are very, very nice rules because basically they can simplify complete parts of the formula by substituting them zeros and ones. After you introduce zeros and ones, you can use them for further simplification. So these rules are also really, really important and very useful. You will check out them in the lecture notes, and I am pretty sure you will understand how they work. Okay, further laws. We have certain rewrite rules. They all about getting rid of such unnecessary operations like exclusive or equivalence, implication. They all of them can be eliminated actually, because for example, XOR can be replaced with a negated equivalence. Equivalence can be replaced with a double implication. And finally, this is the most important one, implication can be eliminated by this guy here. Just exchange implication with disjunction and negate the left hand side of the implication. This is really, really important here to know this one. In the exercise class, we will use this rule so many times, so I'm pretty sure you will fixate this in your brains. If you look at those rewriting rules, it's quite obvious that we will eliminate all those three operators and replace them only with negations, disjunctions, and conjunctions. So this will be a nice side effect of applying laws. Only negation, conjunction, and disjunction remains in our formulas. Okay. Okay. As far as I can recall, you already know what the De Morgan laws are. You learned it in calculus, in your calculus class, right?
No.
No. Okay, that's interesting. Actually, I've heard that Hungarian students learned about this in the calculus class, but in the context of set theory, not in logic. Anyway, these are very nice rules because you can simplify parentheses out. If you have a formula inside parentheses and this whole formula is negated, you can just eliminate the parentheses by moving the negation inwards. So if you look at this, both operands P and Q are negated. And furthermore, this is important,
the negation of and, it will be or.
Exactly, that's it. The negation of and is or, the negation of or is and. Exactly. Great. So this is also a very nice rule, which can simplify your formula. And let me mention this one before we start to solve this exercise together. So there could be laws, though, which doesn't seem to simplify anything. So if you look at this, you start with such a formula and this is what you get. So this is not that
it's even more complicated.
Yes, it's even more complicated, as you are saying. Exactly, it's even more complicated. So it's a good question why we should apply such a rule. But you will experience that sometimes it's worse to make stuff a little bit more complicated and then simplify the resulting formula further. So sometimes we might need such laws as well. Okay, this is the last slide of the logical laws. These are actually additional rules which are implied by the previous 4 slides. I might use one of those in the exercise, but now let's switch to the exercise. Or if you have any question, please raise it now before we start to solve this exercise. Okay, so let's hit the fan. Let's simplify this formula. If you look at this formula, well, you can imagine that it can be simplified. It contains x twice, y twice. We use all kinds of operators. So let's hope we can simplify it. And after we simplified it, let's find out if it is a logical law or it is satisfiable or unsatisfiable, right? So let's find out what semantic properties this formula has. Okay, so let me start with this one. I told you that implications can be eliminated. So do you remember how we can eliminate an implication? Okay.
Wait.
Yeah, what? Could you repeat your answer?
We can negate it with, or we can
Yes.
And
we can replace it with a negated implication, or not implication.
Okay, let's see. So here, yes, you are part right. So okay,
With a negated conjunction.
yeah,
Oh no,
disjunction.
Disjunction.
That's it. Okay, yeah. Here, basically, you can replace implication with disjunction, and don't forget to negate the left hand side, right? Okay, nice. So
Can it be also like we negate the second one and make it and?
this one?
It's like the simplify. When you negate the implication, you can make like x and negation of y.
Okay.
It's the same thing?
It's the same thing. Yeah, let me get back to this point. Good point. Let's discuss about it. So let's first do this rewriting here, and I will show you that what you suggest is also correct. So following this law here, this is how we can do this simplification. But you also told us to do an alternative rewriting. What was that?
X and negation of y.
Negation y.
Okay. So now the question, if both answers are correct, what do you think? Are they equivalent to each other?
I think yes.
Yes. Why? How to
we can check the truth table. It's like and or.
Yeah, or we can further simplify this part here. There is a law for this. So now we have a formula inside parentheses, and this whole
Morgan.
De Morgan, yeah, that's it. De Morgan law. Here it is. So if we have a formula inside parentheses, and now we have disjunction inside, so this one here, then let's negate everything inside the formula. So basically, let's negate negation x, let's negate the logical or, which makes it logical and negate y. And
yeah, it's the same thing.
As the same thing, because we can simplify the double negation out as well. Okay, nice, very nice. So we got the same. And actually what you suggested, this rewriting, is nothing else but two simplification steps, one after the other. First we eliminate the implication here, and then we do a De Morgan rewriting. Okay, nice. Actually, this is, we can find your suggestion at the end of this slide. Okay, nice. Let's continue. So what can be simplified here? It's quite easy to see that this parenthesis here can be eliminated, because we have two conjunctions, and we know that conjunction is associative. Therefore, it's always a good idea to just eliminate the parentheses, because it can make the picture more clear. Okay, now what? Well, there is no other option. We have to deal with this exclusive OR. So it's quite arithmetic what we can do. Let's just rewrite the XOR to this guy here. So XOR is nothing else than a negated equivalence. So, okay. Let's just exchange the XOR to equivalence.
Left, right.
Yes, that's it. Thank you. Okay, and I forgot to put negation here. So it must be a negated equivalence, right? Okay.
Yes.
Okay, let's continue. Now we have an equivalence here, so let's rewrite it to this guy. So equivalence is nothing else than the end connection of implications back and forth. So P implies Q and Q implies P. Therefore, okay. So this is one of the implications we have to use here, and this is what we have to connect with the implication other way around. So
Y.
Exactly, not Y implies X. So this is what we get here inside the parentheses. It's important to keep it inside this parenthesis because this whole stuff must be negated at some point. Let me just put a space here because this part lives their own separated life now. Okay. Okay, what can we do now? How to continue? Let's work on this part.
I think we can simplify the implication also.
Yeah, exactly. This is what we have to do to get rid of implications by using this very nicely decorated rewriting rule at the bottom. So here just use logical OR and don't forget to put negation in front, right? The left hand side must be negated. And similarly, let's simplify the other implication.
Y and X.
Y and X, exactly, that's it.
I mean OR. Don't we also like change the AND to OR? The outside one.
This one?
Yes.
Not now.
Because it's in, or later, after we imply the negate.
Yes, exactly. Let me just keep track of all the formulas. Yes, exactly. So now what we did was only about simplifying the implication. So we simplified this part and that part. We have not touched this conjunction yet, but soon we must do that because we have a negation outside. I guess this is what you meant.
Yeah.
Okay, so how to continue? What do you think? This looks really ugly, so now we
think it will be X or Y and then or negation of Y or negation of X.
Yeah, almost correct. You said or here. It turns to...
We also turns to AND.
Yes. Okay, nice. So basically what law we have to apply here? Which law? De Morgan law, right?
De Morgan, yes.
Again. So basically, if you look at this, how to say, so in this law, in this first law, actually, let me erase the screen, get rid of those red stuff. How to get rid of that? Okay. So basically, what we have to, the formula we are facing to looks like that. No, sorry, this is not true. Jeez. Looks like that. Sorry. Where P stands for this guy here, and Q stands for Q stands for this guy here. So basically, this is what something I wanted to emphasize, that those laws are actually templates. Inside those templates, P, Q, R can be substituted with anything. They can stand for anything, and now P stands for this guy, Q stands for this guy.
Makes sense, actually.
Yeah, exactly. Thanks. Okay, so basically, the law says we have to turn this formula to sorry, to negation P or negation Q. So basically, we negate P, then we use logical OR here, and then we have to negate Q, right? And
yes,
yeah, okay, thanks. And that's it. It looks really ugly, but this is what we get. This is negation P or negation Q. But you already did the next two steps, I guess, because this part we can apply the De Morgan law again, and similarly to this part, right?
yes.
Yes.
Okay, let's see what we get. Okay, so what we get from this?
X and Y.
X and Y, exactly. And of course we eliminate the negation, great. And the next one, what we get from this guy?
Negation of Y and negation of X.
Exactly. Exactly.
You should eliminate also the negation, the outside.
Yeah, thanks. Okay, and this was what you suggested, as far as I remember.
Yes.
Okay, so you did the smart thing. Actually, you applied De Morgan laws 3 times inside your brain, and yeah, congratulations. Actually, this is easy to do, because let's look at the formula which we simplified to this formula here. So if you want to move a negation inwards, basically everything inside is negated. Negation X turn to X, or turn to AND, negation Y turn to Y, and turn to OR, and so on. So you can just negate everything inside and you immediately can get the result. Okay, guys, so how to proceed? Can we further simplify this? This is a good question. So if you ask me, we stuck a little bit. It's not obvious how to continue or it's not obvious if we can simplify this formula further. If you look at it, it feels like, yeah, probably we can, but how? So this is the exact situation when we need to apply an ugly rule, and this is distributivity. So if you stuck, probably you have to apply distributivity. It rearranges the formula a little bit, and then we hope we can simplify the formula further. So what this law is about, let's see. So it's basically about how to say, drawing pairs. I'm pairing P and Q, and then I'm pairing P and R. So I try to generate all the possible pairs outside and inside the parentheses. So this is how you get P or Q. So you connect the pairs with the the outer operator. Similarly, we get the other pair here, and then we connect the pairs with the inner operator here. If you check out the lecture notes, there I'm mentioning a similar property of multiplication and addition in mathematics. Anyway, this rule also works if you have not one but several stuff here, like X and Y or Q and R.
I think this will be big, like to just simplify it.
This will be big. This is what you said?
Yes.
Yes, it will be huge.
It's like you're adding X and Y, or X and Y, then you add it to Q and R, and then you add X. It's very big.
Yeah, so it's actually, it will be huge because we draw all the possible pairs, X or Q, X or R, Y or Q, Y or R, right?
Yeah.
Okay. So basically it turns to X or Q, X or R, and the same with Y. That's it. So it's really ugly, it's really huge, but actually in this case we have to apply this rule, and you will see it will work perfectly. So let's see. Whew. Okay, so let me erase this here, and let's build up the formula step by step. So here I have to draw a pair of X and
X or
yeah, okay.
negation of
X or
negation of Y.
Negation of Y. Nice. This is the first pair. X and not Y connected with OR. Yeah?
And
very good. So the pairs must be connected with logical AND. Yeah?
X or negation of X.
That's it. This starts to look really good, actually. Okay, the third pair.
Y or negation of Y.
Okay, and finally.
And Y negation or negation of X.
Yeah, thanks. Okay, guys. Does any of you have question? Because this rule, the distributive rule, is the one of the most difficult ones. Okay, so actually in the practice class we will apply this rule and also De Morgan rules and all the others plenty of times, so I guess you will get used to them. Okay, that's it. So we made the formula much uglier. So let's try to simplify. First of all, before you give me hints. So first of all, if you look at this formula, it's a bunch of conjunctions, and actually we have conjunctions also outside of the parentheses. Therefore, we can nicely eliminate this outermost parentheses because we have 1, 2, 3, 4, 5, 6 expressions connected with conjunctions, and conjunction is associative, therefore it does not matter in what order we connect those 6 elements, right? Okay, next step. What do you suggest? How to simplify the formula further?
Y or negation Y.
Yeah, that's it. Y or negation Y.
And X or negation X.
Yeah. The both. This one and that one. So they
both. It's always 1.
It's always 1. Are you sure?
X or negation X.
Mm-hmm.
Yeah.
So, yeah. Okay. Nice. So this is what we call the law of excluded middle. It means there is no third option. Only those 2 options are possible. So their OR connection is true. Exactly. Okay. Similarly, as you suggested, Y or not Y can be simplified to 1. Okay, so now this is getting quite nice. So what to do with this one? First of all, we can eliminate one of them because no duplications are necessary. Yeah? Go ahead.
We can eliminate the second 2. Okay. Oh, no.
Yeah, I already did that.
Yeah.
Okay, and what to do with the remaining 2? Can we?
It can be eliminated too.
Yes, exactly, because we have this law of well, this is it, law of identity actually. So for conjunction, 1 works as the identity. It doesn't change the other operand. So if you think about this, 1 can be eliminated. Great. So yeah, that's it. Okay, so if you look at this formula, basically we eliminated the two middle formulas. This is what you did, and this is what you get. Okay, so what to do with this?
X or negation Y and X and negation Y.
Mm-hmm.
I think.
So you are telling X or negation Y can be simplified with X and negation Y?
Maybe.
Yeah, actually you are right, with the extension that actually X or negation Y can be simplified with only X. Negation Y is not needed. Or you can use only negation Y to simplify this part. Okay, this is the law. This is possible because of the law of absorption. So if you look at this formula, Okay, sorry, this formula here. So we have some kind of formula like this one, where we have a conjunction outside, disjunction inside, and the same formula is repeated outside and also inside. So let's see. So here P stands for X and Q stands for negation Y. Negation or the other way around. So negation Y appears also outside and inside here.
Yeah.
And do you remember what can we do now?
You can just use like negation of Y.
Yes, exactly. So basically
we eliminate
eliminate
X or
this
negation
one.
of Y.
That's it. That's it. Exactly. So we eliminate this one always and keep only Q, which is negation Y.
And we can do this is negation X.
Excuse me?
I mean, I thought that we can also eliminate the other one, but it's negation X and X.
No, exactly. We cannot eliminate this one because we have Y inside, but negation Y outside, and similarly we have negation X inside and X outside, so they are not the same. Absorption only works if you have the same inside and outside. Yeah, good point. So here we are. The question is if we can simplify this formula further, or that's it. This is the simplest form of the formula.
I think that's it.
No, we can simplify it further. We can simplify it further. Let me give you a hint. We have to apply a law. We have to apply law in a reverse way. So we rewrite the right hand side to the left hand side. And I'm intentionally showing you this slide. This is not that obvious anymore. So this is what you need intuition and some experience.
I understood. It's X and negated Y equals to negated
That's it.
Y and negated X.
I think you are on the good track. So it's negated what? So you are telling this part, X and negated Y, is the same as what?
Negation X or Y.
Like this one.
Yes, they're the same.
Okay, this is what you meant?
Yeah, but we eliminate the outer negation because we add it inside.
No. Actually, this is the reverse application of this, De Morgan law. So you have to add a negation outside of the parenthesis. Here it is. And yeah, and you have also to negate everything inside the parenthesis.
And P and negated P is always 0. So
you are talking about the next step.
yeah.
Yeah, this is always 0. Why is that?
Because the formulas in parentheses are equivalent to each other.
Mm-hmm.
And
yeah, they are equivalent.
Yeah.
You mean you can if it makes easier for
yeah,
all
it
of
can
us,
be switched.
it can be switched because this is a commutative operation. I mean logical order. Yeah, and they are the same, right?
Yeah, they are the same, and P and negated P equals 0.
Yes, exactly. Very nice. So this is the law of what? Law of excluded middle again. If you have sorry. This is the non-contradiction law. If you have something and you negate that something and you connect both with conjunction, then this is always 0. Something and its negation cannot be true at the same time. That's it. Very nice. So basically, if we apply this law, P stands for this guy.
Exactly.
Okay. And we apply this rule. Okay, guys, that's it. That's the end of the story. So, of course, we cannot simplify this further. This is the simplest form of this formula, but it's kind of, I mean, amazing how we were able to simplify this ugly formula to this single 0 at the end. This is sometimes possible. Okay, do you have any question, guys?
Yeah, it's complicated.
Okay, this was not a
It's not simple. You don't make it simple, you make it complicated.
Oh,
yeah, well, in this case, I'm not sure it's worth to use this approach. I think it would be easier to use the truth table because we have we have only 2 variables, so this means the truth table has only 4 rows. But just imagine that in real life we have huge formulas with thousands of variables or even more, 10,000s and hundreds of thousands of variables. So for them, truth table is not an option. Only this approach works. Yeah. So next time we will learn how to make this as automated as possible. Because it seems not that automated. So sometimes we have to think about which rule to take, which law to take, how to apply it in a forward or a reverse order. So the human factor seems to play a role here. But next time you will see that we have a nice algorithm for simplifying formulas in a nice way. Okay, and let's not forget about this question. So what do you think? What kind of formula do we have now?
it's unsatisfiable.
Yeah,
Yes,
unsatisfiable.
unsatisfiable, great, because it's always 0. Okay, guys, so this is the end of my slideshow. Yeah, so again, please read the module and solve the exercises and solve the closing test as soon as I will send you a message about it's already completed by me. Let me check if all of you set your email addresses here. Just a sec. Okay, so we have Ahmed here who have not set his email address, nor Destiny did. Danny, Rasul, you did not set your email addresses. Therefore, if I send a message to you from the e-learning side, you might not receive it. So please click on your profile page here, profile page, and set your email addresses. Okay.
Okay.
Because I will send you a message as soon as I completed the module and also this closing test. Okay, next time we will continue with the next topic. Let me give a spoiler to you. So this will be about so-called normal forms, and this is why I referenced to a minute ago. So we will learn an algorithm about how to apply these laws one after the other to make everything as automated as possible, and as the result we get a simplified formula, and a formula which is in a good form, a normal form, a very advantageous form we use in which is really transparent and is used by solving softwares in real life. So this is the topic for the next lecture. Okay, that's it. Thanks for your attention. At the end, any question or notes? Nope.
No questions.
Okay, whenever you have any questions, you can type it in the text channel. I'm trying to respond. Okay, thank you. So have a nice week.
Thank you. Have a nice week, you too.
Thank you.